Okay, hi there, Dr. Matthew J. Trom here. Um, we are in a new module. So this is module 4, transient conduction, and lecture 9 for the summer is called lumped capacitance. This corresponds to chapter 5 in the textbook. And we've got 5.1, 5.2, and 5.3. Those are the sections that this lecture will cover. Um, for those of you potentially looking for the ADA compliant transcription, I'm making the recording right now. So once the recording is done, we'll have a Zoom generated transcript, and I will, when I finish these slides, drop the link here, which will give you access to that transcription if you're looking for it. Okay, so oh, I guess one thing that I want to mention, and this is particular to the summer. Um, I got a little bit behind where I wanted to be, and so I'd actually assigned this reading like weeks ago, like before summer break, but didn't actually get the lecture put together, and then we had to jump around a little bit because we had to get prepared for the hosted by Sandvik and then hosted by GE Vernova portions of the class. So we got into heat exchangers and stuff, and so this might feel like backtracking a little bit because we're now up to chapter 11. But that's why we're doing this now. Is I didn't actually do the lecture for this. I just did the reading assignment. So we're a little bit out of order, but that's okay. That's okay. It's there actually are heat transfer textbooks that right after um, steady state conduction, they do heat exchangers, right? That's actually the recommended, not required, but recommended textbook, which is an OER from John Leonhard at MIT, actually does it that way. So this is not catastrophic, not devastating, but just wanted to point out that we're a little bit out of order from what I'd originally planned. Anyway, it'll be fine. Okay, so uh-oh, can I change slides? Yes, I can change slides. So let's get my laser pointer going. There we go. All right. So as you know, I like to start all my lectures with a cartoon or a meme or something relevant. And this popped up in one of my social media feeds, and I thought this was quite funny. So here we are, right? But you can kind of see what's happening, right? It's hungry engineering student after a 3-hour heat transfer lecture, and I kind of like this because this implies that the 3-hour lecture was done on a computer, right? So because we're at least in the summer remote and asynchronous, and so you guys are watching this in this exact same format. And my lectures tend to run pretty long because I try to do like an entire chapter in a lecture and cram that all into one. So you probably do sit for 3 hours and listen to me. Hopefully you put me on, times two or times three, so you don't have to sit there and listen to me for hours on end. But anyway, after 3 hours, you're hungry, and so what do? You take your like computer chargers and your power bricks, and you make a little like sandwich, and you end up heating, I don't know what this is, a hot pocket or something between your computer chargers. So anyway, I just thought this was funny. So there you go. All right. So I had my own version of this slide. This is it was meant to be the introduction to transient heat conduction, but my version of this slide was just all text. It was like a wall of text, and so I fed the wall of text to the Terminator, to AI. And this is what it generated. And so I'm trying to be better about using AI to make slides like this. I checked it, and I'm pretty sure that it's error free, although you never really know with AI. But I'm going to use this slide kind of to anchor all of the discussions that we're going to have um, about transient heat conduction. So the big kind of takeaway message is, up until now, we've assumed that everything is in steady state, right? Once a temperature profile is in a solid it's fixed, and it doesn't change with time. There's a whole like set of problems, which is what we're going to get into now, where the temperature profile does actually change with time, and steady state is no longer assumed. So these are called unsteady or transient problems, and essentially what the hallmark of these things are is that you are somehow changing the boundary conditions with time, right? So you have some initial set of conditions, and then you change it, and the system responds to that change. Now, that change can just be like I'm going from one temperature to another and I'm done. Or the change can be, some more crazy stuff like I'm heating and cooling periodically, or like heating and then moving like that source of heat around, on the surface of the object. So it's basically just anything where the boundary conditions that cause heat transfer to the object are not constant with time. That's a transient problem. Um, and there's kind of four different sections of this chapter, and for this lecture, we're going to talk about this one, and then the next couple of topics we're going to do in a different lecture. But lumped capacitance kind of makes sense all by itself, so we'll do a lecture on lumped capacitance. So what lumped capacitance is it's the underlying idea is that spatial temperature gradients are neglected. So you've got some object, and you're doing something, like I mentioned, to change the temperature of the object with respect to time. But the trick with lumped capacitance is the entire object uniformly increases in temperature or decreases in temperature. There's no spatial directional temperature gradients. It's just the whole thing gets hot, the whole thing gets cold. Um, and so that's what this says here. Temperature is uniform throughout the body at any instant. And so this is like the holy grail, right? It's like if you can model like, and there's a criteria which is called the BO number, which we'll get to in this lecture. But if you can demonstrate that this BO number is less than zero point 0.1, criteria is met for your object, then you are in a happy place, my friends, because lumped capacitance, you guys will see mathematically, is really easy. It's, relatively easy compared to all these other things. It does involve, exponentials and logarithms and kind of it's a little bit of nasty math, but nowhere near as nasty as these other things. So anyway, that's what we're going to talk about today. Then there's these other things. So finite solids. This is a situation where you have to deal with both a spatial temperature gradient, so like different directions, right, have different temperatures depending on where you go in the object, and a change in time, right? So you can basically imagine, right? It's more complicated because you're dealing with both a temperature field and the fact that the temperature field is changing with time. So we'll do that next time. And then there's this kind of unique class of objects called semi-infinite solids. And these are, well, I mean, they're semi-infinite, right? So kind of characterized by this impossible feature of being infinitely long. But, as we saw with fins, you can have an object that is modelable as being infinitely long, but it doesn't have to be infinitely long. It's just it reaches a certain point where the heat transfer just doesn't matter anymore because it's reached, some sort of constant temperature or temperature parity with the environment. And so we'll talk about those later on. And then this is a transient thermal response. So represents transient thermal response, variety of objects, step change, blah blah blah. Right. So this is like I basically got the system set up and I'm messing with the temperature profile, changing the temperature profile as a function of time, right? So it's I've got one set of conditions and everything kind of settles, and then I all of a sudden boop change it to something else, and then I can change it to a third thing. And so this is like if the boundary conditions are changing in time, like how do you deal with that situation? So anyway, I won't go over this slide again, but I will use it, as I said, in previous future lectures to kind of anchor, like, where we are in this progression from lumped capacitance to finite solids to semi-infinite solids to transient. Okay, and if I didn't mention it before, this is an AI generated slide, so okay. Um, Lumped capacitance. So as mentioned, um, solids can experience subtle Sudden, solids can experience sudden, there we go, thermal environmental changes, and their internal temperature responds accordingly. The hallmark of lump capacitance, as I said before, is there's no internal temperature gradients, no thermal gradients. So the entire object is exactly the same temperature from spatially, right? Exactly the same temperature all throughout its solid body from one moment to the next. It can change temperature in time, but the whole thing changes temperature uniformly. And so the classic example of this is if we have a chunk of metal and it's heated up, and we're quenching it by basically putting it in a cold liquid, and that quenching event happens at time equals 0, and the object is hot and the liquid is cold, right? So here's the temperature, uniform temperature of the object, Ti, and then here's the liquid, and the liquid, of course, is at a lower temperature than the metal. Um, and so if you take this hot metal and you dip it in water or whatever, cold liquid, eventually it'll cool down and it'll reach T infinity, that liquid temperature, right? So there's in this system, there's an underlying assumption that the thermal mass of the water is basically infinite, right? It's big enough that it doesn't change temperature, even though there's a bunch of heat that's basically getting sucked out of this piece of metal into the water. So the essence of lump capacitance, as I've said, is that solid internal temperature remains spatially uniform during transient processes, and therefore temperature gradients within the solid are negligible. This, of course, creates a paradox if you're kind of thinking through this logically, which is if you have uniform temperature all the way across, remember you need a temperature gradient to facilitate heat transfer. So if you have like uniform temperature all the way across, how does that facilitate heat transfer? There's no way for the heat to get from the inside of the object to the outside of the object to get into the water if the temperature is the same all the way through. So clearly this is an assumption, right? This is a model, a mathematical model, that's representative of the real situation, but not quite right. And we'll see that there will come a time, not in this lecture, but later on, where you realize that this idea of like uniform spatial temperature isn't quite right, and you have to in some cases correct for it. But if you can assume lump capacitance, and like I said, I'll show you the criteria in a bit, um, you can assume that there's no temperature gradient internal to the object, and the math works out fine, even if physically it doesn't really make sense given everything that we've already learned. Um, so that's why the temperature gradients within the solid are negligible. Okay. So what do I say here? Transient temperature response from the energy balance. Oh, okay. Yeah, right. So the transient temperature response that you can come up with a mathematical model for comes from just performing a first law energy balance, right? Just thermo on the object. And so this balance basically relates the rate of heat loss at the surface to the rate of change of internal energy, right? So you look at the object, you draw a control system, right? Control surface around the object. Inside is a control volume, and then you allow heat transfer across that surface, which then drops the internal energy of the piece of metal. And the drop in internal energy has a corresponding reduction in temperature, at least in this case, if we're cooling. So that's where it comes from. Okay, so let's actually do it and see what happens. So here is my system, right? And I'm gonna draw my control surface like we did in thermo and fluids and so forth. We always do that. And then I'm going to apply the first law of thermodynamics, right? So I don't have any mass flux here. This is a closed system. And so it's the closed system version of the first law. And of course, something is changing, right? Internal energy is changing. And so I need the time dependent version of it. So I've got dE dt is equal to W dot in minus W dot out plus Q dot in minus Q dot out. And as I think I've told you guys before, right? Whenever you write the first law of thermodynamics, please write it this way. Do not write that delta E equals Q minus W nonsense. That is not correct. You get taught that way because people are lazy and they like to just write a few things. But that delta E equals Q minus W is only true for cycles, right? And this is not a cycle. So write out the entire equation, even if it's kind of onerous to do that, because otherwise you'll mess this up. So um, much better to cross out the terms and actually know what you're doing and why, than just trust some sketchy thermo professor from 2 years ago, right? So okay, so no work, right? So the work terms go away, or the power in this case terms go away. There's heat leaving this thing but not entering, so Q dot in is gone and Q dot out stays. So what I'm left with is delta E delta T, or dE dt, is equal to minus Q dot out. And this is, again, closed system. So the internal energy is just, or I should say that the energy of the system is just the internal energy of the system, U. And hey, it's a solid. So we know that the internal energy of a solid is the mass times the specific heat times the temperature. So if I take the derivative of that with respect to time, I get the mass, right? So rho times V is mass. And then here's the specific heat. And then here's the temperature. And I'm taking the time derivative of it. These things are assumed to not change with time, or temperature in that case, or for that case. And so they come out of the derivative, and I'm just left with d temperature, d time, on the left or the right hand side. And then on the right hand side, what is this Q out? Well, that's the amount of heat that has to get convected away, right? This is liquid water, right? So there's convection on that surface. So we're going to use Newton's law of cooling, right? So convective heat transfer, which is this. And then this negative sign comes from there. And you guys have seen Newton's law of cooling before for convection. Okay. Oh, and I say here, assume material properties remain constant, right? So that's what allows me to pull rho VC out of the derivative here and just leave dt all by itself. Okay, so in these transient problems, there's a technique, which you guys have heard me say this joke before, right? It's the law of conservation of chalk, which when I was a lower division mechanical engineering student, actually aerospace engineering student, my chemistry professor used to make that joke that, like, we would just write things in more compact ways, and it was the law of conservation of chalk. And so I'm, carrying on the tradition. So we're going to define this thing called theta. And theta is just a temperature difference, right? So it's the difference between the temperature at a particular moment in time for the body minus the temperature of whatever fluid it happens to be immersed in. We're going to call that theta. And notice if I take the derivative of theta, so here I am taking the derivative of theta with respect to time. It's just the derivative of temperature with respect to time, right? Because this changes with time. This is constant with time. So if I take the derivative of the whole thing, this goes away, and I'm stuck with just the derivative of this, right? So those two derivatives are equal to each other. Same slope, same slope. The only thing that's different between them is just the starting point, which is this term. Okay, so now that I've got theta defined, I can go back up to my original equation, and I can say, look, here's theta right here, right? Ooh, and here's the derivative of theta right here. Ooh, okay, cool. So I'm going to plug those in, and I get this guy. And now this is solvable, right? I basically got rid of this T infinity term, and now I have a solvable differential equation. Which is just separation of variables, right? So I move everything to one side of the equation that has to do with time, move everything else to the other side of the equation that has to do with theta. All of these terms kind of just get bunched together, rho VC over HAS, but those are all constant. So when I actually carry out the integration, they come out of the integration as a constant. And basically what I'm doing is integrating from some initial time to some final time. Remember, this initial time, we set that at 0, right? So that's the moment that this thing gets immersed in the water as time equals 0. And we're just going to leave it in there until time equals t, whatever that is, right? And then that actually gives us an equation that's a function of t, allows us to plug in a value for t for time to figure out, like, what the temperature is at that time. So that's this integral. And then this guy, we're just, right, remember, because the integrand here is theta. So we're integrating from theta initial to just theta. Theta initial, if I go back here and remind myself what theta was, theta initial is just when this temperature is whatever the initial temperature of the object is right before it got quenched, right? So that I for initial is just, T initial minus T infinity gives us theta in I, theta initial, and then theta is just this, right? So theta is the difference between whatever the temperature happens to be at time t minus whatever the temperature of the bath is that the hot object got dunked into. Right. And then this is all constant, so it'll come out. And then we have d theta over theta. If I take the integral of d theta over theta, I get logarithm. And so here's that logarithm. This is right. Remember, we're subtracting. If you remember, carrying out these integrations, right? I solve for whatever this thing is, ln theta this minus ln theta this. And in the world of logarithms, a subtraction is a division, right? So that's why these things get divided by each other. And this guy just integrated to t. And so voila, this thing comes out like so. And notice, right, it's this minus this, and yet they're flipped over. And that's because I had a negative sign here, and that negative sign is gone over here, right? So that causes this division to flip over, to cancel out the negative sign. So that's my solution. And then to make it easier to solve, I just exponentiate both sides, right? So I end up with just theta over theta initial, right? Which I've now broken back out into t minus t infinity and t initial minus t infinity, so that you can see the relationship between temperature with respect to time, and then this exponentiation. And it's just e to the minus ha over rho vc times t. And A is the exposed surface area, so the area that this convection is happening over. H is the convection coefficient that's facilitating heat transfer. And then rho is the density of the object. V is the volume of the object, right? And rho times V is mass. And then C is the specific heat of the object. And then this lowercase t, that's time. And so now I have an expression that gives me the temperature of this object once it gets immersed for any positive time, lowercase t. So that's it, right? That's right. So this isn't that bad compared to some of the other things that we've seen. So that's the solution for lumped capacitance. Now, let me see if I can get the slides to move. There we go. Okay. So let's dig in here a little bit deeper. So we've got this expression for lumped capacitance that we just derived. And a couple things to point out, right? If you allow this time to basically go out to infinity, what we're tracking as this time gets bigger and bigger and bigger is the difference between the solid temperature and the fluid temperature. And that difference essentially decays to zero at t is approaching, or t reaches infinity, right? And you can see that, right? Because what's happening here is if this number gets really big, this negative sign makes this exponent very large but negative, and e to a very large negative number basically goes to like 1. And then this thing becomes oh, no. T to a very big negative number is 0, right? Yeah, blah, 0. It's like, what? So this guy comes over here and gets multiplied by 0. And then what you end up with is that t at some infinite time is basically equal to t infinity, right? Okay. Ooh. Whew. Saved myself from a disaster there. So that works out fine, right? That's what you would expect if you have this object and it's in this water bath for a really long time. Eventually it's going to reach the temperature of the water bath, which is exactly what the math says here as t goes to infinity. So that works out good. The next thing to look at is this exponent, right? And to note that this whole thing can be represented as a thermal time constant. So sometimes just represented as tau t instead of all these variables, right? It's more law of conservation of chalk, but sometimes it's done that way. Another way to look at it is if you take 1 over HA and then rho VC. This, right, recognize this, it's 1 over HA. That looks like a resistance, right? And then rho VC, yep, looks like a capacitance. Um, and so we can actually write this exponent both as this kind of time constant, but also as the product of a resistance times a capacitance. And so I say here, you can write this time constant as RTCT, where RT is a convective resistance to heat transfer, right? 1 over HA. And CT is a lump thermal capacitance of the solid, right? The ability of the solid to absorb thermal energy. Increasing the resistance or increasing the capacitance causes the solid's response to slow, right? So it basically gets more, right? As this number gets bigger, it's more thermal mass, right? As this number gets bigger, that means the convection coefficient is going down, right? So less heat transfer. And so those two things, either one of them will cause the overall process to slow. And this is analogous to what you see in voltage decay when you have an RC circuit, right? A capacitor discharged through a resistor, an RC circuit. So here's a visual image of this. So we have on the x-axis time, on the y-axis we have our dimensionless temperature, so theta over theta initial. And as I mentioned here, as R times C increases, right? So here's an arrow for increasing direction. The temperature response of this object slows down, right? So it eventually will get to theta equals 0, right? Which again is that this guy equals this guy. But it happens much faster if RC, this exponent, is smaller, and it happens slower as this exponent gets bigger, right? So hopefully that's intuitive, and you remember that from your circuits class. Okay, next. So now remember back from conduction, right? You always want to know both the temperature field and the heat transfer, right? The Q. And so same is true for lump capacitance. So now we have a way of figuring out the temperature field relative to time. And now we want to figure out how much heat was transferred from the system in some amount of time. So to do that, we want to just integrate so I'm going to go all the way back to, right? I'm going to go all the way back here, right? And I'm looking at this expression and remembering that Q dot out minus Q dot out is equal to dE dt. And if I get dE dt and multiply by the time difference, the elapsed time for the quenching process, what I'm left with is just the energy, right? So I basically want to take Q and integrate it, and that gives me E, which is what I'm doing here, right? So here I've got Q dt, and then I've got Newton's law of cooling on the other side, and I'm integrating this from uh, let me, I might need to, here, I'm make a note to myself that this slide might need some help. Like, what is this delta T thing? Oh, no, no. Oh, no, this is okay. This is okay. Yeah, sorry. I'm like, what is going on here? Yeah, sorry. This is fine. I'm taking Newton's law of cooling, and I'm just multiplying both sides by, right? So let's go back. So I'm taking just this, right? And I'm multiplying both sides by time, right? So I've got Q on one side of the equation, and then I've got HA theta on the other side of the equation. And I'm multiplying both sides by an infinitesimally short time, and then I'm integrating over some time from 0 to t on one side and 0 to t on the other side. Okay, whew, that's fine. I can do that. Okay, and then what happens? Well, so I get big Q, right? So this is the total energy that gets transferred away from this object. That's just the integral from 0 to t of lowercase q dt. And then on this other side of the equation, I get, if we go back, right, it's all this, right? Because this guy equals that guy equals Q. And so here's my rho VC, and then here's my theta, and then here is um, I'm taking my expression from for theta from here, right? Or here, and plugging it in here and then doing the integration, and this is what pops out, right? So this is my value for Q. So if I wanted to know how much total heat got transferred away by quenching this object over some amount of time, I just take that amount of time, I plug it in here. Here's my time constant, right? RC or um, rho VC over HAS. Plug in the value for T and now pops Q. And then as promised, right, that Q is just the amount of energy change in the system. Okay. So we can now, using lump capacitance, figure out the temperature at any time, and we can figure out how much heat was transferred out or into our object for any time. So we have those two kind of pieces in our arsenal. Okay, so I would love to just be able to do this every single time, right? Because it's pretty easy. The math is not too bad. The challenge with lumped capacitance is, as we talked about before, because of that underlying assumption that there is no internal temperature gradients, and therefore there cannot be any sort of conduction from the inside of the object to the outside of the object. If you think about from the heat transfer perspective, what's possible. Lumped capacitance, as I say here, is simple, convenient, and wrong. But despite the wrongness of having uniform temperature on the inside of your object, the math is often accurate enough for engineering purposes. And so, just like we do with boundary layers and other things where we kind of set an arbitrary criterion for reasonable accuracy, we need the same thing for lumped capacitance. And so the way to kind of get your mind around that is a little bit counterintuitive, right? Because we've been talking about like temperature change with time, and so let's go all the way back to a steady state conduction problem through a plane wall. And this feels counterintuitive, but it'll make sense in a second. So remember, in this situation, it has one surface that's like far away from the surface of interest, which is at TS1. The other surface is exposed to fluid at T infinity, right? So I've got TS1 over here, and then I've got fluid flowing here at T infinity. And T infinity is definitely less than T surface 1, right? So you've basically got a temperature profile where the temperature is dropping through this solid object from x equals 0 to x equals L. So this surface is exposed. And it is not going to be at T infinity. It's going to be at some intermediate temperature, which we call TS2. And so T infinity is less than TS2 is less than TS1. So it's cold here, it's warm here, it's hot here. Okay. And then if we do like we've done before, the energy balance on just this little sliver of the surface and set the conduction entering that surface, right? So Ka over L minus the temperature difference between this side and this side, set that equal to the amount of heat that's being convected away, right? So that's just a first law energy balance on this little infinitesimally thin slice where Q conduction in equals Q convection out. I can now rearrange these things. And I might need to change this. This is slide 8. I can rearrange these things. So I have TS1 minus TS2 divided by, this should say TS2 minus T infinity, right? So I just copy pasted this, and that I did that wrong. But what am I doing? I'm just taking this guy and moving it to this side of the equation, and this guy and moving it to that side of the equation, and then writing everything in terms of thermal resistances, right? So that's how I know that this denominator is wrong. Okay, so now that I've got it written in terms of thermal resistances, I can like cancel the areas, move things around, and I get this HL over K expression. And this is the BO number. This is the thing that I was talking about. Remember on my AI killer slide, this one, right? Here's that BO number again. So now you can see how it's derived. It's basically just ratio of temperatures. And notice what these temperatures actually mean, right? So this temperature is representative of the internal temperature gradient from the internal wall of this solid to the external wall of this solid, right? So if there's a big temperature gradient here, then you've definitely got a spatial temperature gradient that you have to worry about. This one is the temperature difference between the wall and the exposed wall and the ambient environment, right? So your BO number is essentially just a dimensionless temperature ratio where you're looking at um, in the numerator the internal temperature profile, and then in the denominator the external temperature profile, like how much delta T is there, like pulling heat out from the surface. Um, so that's the BO number. And what it actually does is measures the internal solid temperature drop relative to the temperature difference between the solid surface and the external fluid. And it turns out, oh, okay, we'll get there. What I was about to say is it turns out that there's a criteria for quote unquote small, and that small BO number is any value less than 1/10, 0.1. So if you have a BO number that's less than 0.1, then you can do lump capacitance. So you can use all those equations that we just talked about. Um, and it's not exactly right, but it's close enough, right? Good enough for engineering approximation, for engineering work. So I say here, BO number is also interpreted as a ratio of resistances. We saw that back here, right? These two resistances. Um, if the BO number is much, much less than 1, that means the resistance to conduction within the solid is much less than the resistance to convection in the fluid. If the resistance to conduction in the solid is very low, that means the solid cannot maintain a large internal temperature profile, right? So if you kind of think intuitively about what that means, it tracks with everything that we've already talked about. And this sets the criteria for assuming validity of uniform temperature distribution. Okay, and so this is what it actually looks like, right? So here we've got our kind of slab wall, and it's got two sides that each have fluid blowing over it with temperature of T infinity and a forced convection coefficient of H. The wall is minus L to L thick. And if we have our BO number much, much less than 1, what that means is the temperature is basically uniform all the way across, right? So if we start at elevated temperature, and then we start blowing this cold gas, on either side of this block, the temperature drops, and then it drops further, and then it drops further until it reaches almost uniform temperature. But notice that these lines are relatively flat, right? Not perfectly flat, right? Because this is an approximation, but pretty darn flat and reasonably good to approximate that as just a constant flat line. And so that's what we get when we have BO number much, much less than 1, is that the spatial temperature inside the object is uniform. So that's what you're seeing visually there. If the BO number is equal to 1, that criteria goes out the window, right? You can see here's my initial temperature, and then I start this process with the air blowing, and immediately I get a spatial temperature gradient from the inside hot part of the wall to the outside cold part of the wall. And so that definitely cannot be imagined to be constant, because it's BO number is 1, and so there is the ability of this wall to maintain a temperature gradient from its interior to the edge. So not constant. And then things just get worse, right? So as the BO number gets bigger and bigger, like bigger than 1, the walls almost immediately fall to whatever the free stream ambient temperature is, where the internal solid holds on to its energy, right? So there's a pretty significant resistance to heat transfer across this wall. And that's what's causing this large high temperature in the middle, and then T wall being almost equal to T infinity. Okay, so hopefully you've been able to like visualize that as I walk through it. So there's one mystery that remains, which is what is this L sub C? When we looked at the BO number before, it was just L, right, which is like the length of heat transfer, or the length of the thickness that facilitates conductive heat transfer inside the object. So what is this C? Well, it's C for characteristic. So we want to define, so it's sort of like a hydraulic diameter in the world of fluids. So we want to define this characteristic length, L sub C, and we want to be able to come up with an L sub C for like any geometry, right? So any shape. And so we have this kind of generic definition, which is it's the ratio of the solid's volume to its surface area. So LC is equal to V over AS. I should put a hash mark through this V to make it consistent. So I'll make a note to do that. Normally, if you had me for fluids, I put a hash mark through a V that's a volume to differentiate it from a velocity, and I forgot to do that in this equation. So I'll put it in there when I fix this. And so that's your characteristic length for a solid of any shape. Okay, so if we apply this formula to a couple of common shapes, like a plane wall, it turns out that L sub C is just equal to L. That's true if your wall is 2L thick, like the wall that we've been talking about, right? So the characteristic length is half the thickness, or L in this case. Right, and that makes sense, right? Because we're looking here at the temperature profile, and the X equals 0, right, is L from the edges, and that's the spot where the temperature is the highest, right? So that's sort of my characteristic length is half the width or half the thickness of this wall. So that one makes sense. If I plug in these numbers for a long cylinder, I get the characteristic length is R naught over 2. And if I plug in for a sphere into this formula, I get the characteristic length is R naught over 3. So R naught, by the way, is just the outer radius of the cylinder, or the outer radius of the sphere. The reason that I put these here, I do not use these, right? So whenever I calculate a BO number, I always want to be as conservative as possible. And so I say here, to implement the criteria as conservatively as possible, so that you're basically assured that you've got lumped capacitance, no questions asked. You want to associate LC with a length scale corresponding to the maximum spatial temperature difference. And so for me, when I do these kinds of problems for a long cylinder, that's the radius, right? And for a sphere, it's also the radius, because if you think about it, right, like a cylinder, just like this drawing, right, the center line of the cylinder is going to be where the temperature is the highest, and then as you move towards the edges, move towards the outer radius, that temperature profile is going to spread out the same way that it does in these drawings. So I use L sub C equals R, both for cylinder and a sphere, because that'll give you a higher BO number. And if you're still less than 0.1 for the higher BO number associated with these conditions for L sub C, then you're basically assured that the BO number is going to be less than 1, even under the like less rigorous conditions. So that's what I would recommend. Just always use these. Don't worry about these. The reason that I put this in here at all is, one, it's in the book, so I don't want to confuse you, and two, there are like tables for BO number and the relationship between BO number and other numbers that we'll calculate later. And sometimes the tables are formulated in terms of, for cylinders and spheres, in terms of the radius, and sometimes they're formulated in terms of characteristic length. And so you do have to be careful when you're looking at the chart to make sure that it's not R over two, or if it is R over two, you're aware of it for a cylinder, R over three for a sphere, and not just R. So just kind of a word of warning that might come up, and you just have to be aware of which which of these two definitions is being used by the book to generate the table that you're using to do the lookup of properties based on BO number. Okay, um, so um, we're going to just quickly introduce another dimensionless number. If I didn't say it before, let me say it now. The BO number is dimensionless. Okay, said it. Fourier number is another dimensionless number, and the Fourier number is basically a non-dimensional time. And we're not going to use it so extensively in this lecture, but it will definitely play a central role in an upcoming lecture because the Fourier number determines if your BO number is right. You're probably asking yourself, what happens if the BO number is less than, or sorry, greater than 0.1 instead of less than 0.1 if this criteria is not met? Well, what that means is that you have to deal with a spatial temperature gradient, right? Like I've shown here. And then there's this second dimensionless number called the Fourier number, which will work into how fast the temperature profile decays. So like I said, it's a dimensionless time. And it turns out, it's a little bit counterintuitive, but the Fourier number is actually buried in the exponent for lumped capacitance, which is kind of funny because lumped capacitance and the Fourier number are like diametrically opposed. They very never show up together because if you can do lumped capacitance, you don't need the Fourier number and vice versa. But it turns out that the Fourier number is actually in lumped capacitance. And the way to get to it is to recognize, okay, we've got this definition for LC, which is the volume over the area, surface area. And I'm going to take that definition, I'm going to plug it into my lumped capacitance exponent, right? So here's LC in the denominator that comes from this being plugged in for here. And now I'm going to try to isolate the BO number all by itself, right? So I'm going to take H LC over K. However, there's an LC in the denominator and there's no K here. So what did I have to do? Well, I had to multiply the top by K to get a K in the bottom. And then I had to add an LC to the bottom, to the denominator to get an LC in the top. So that's where this intermediate step comes from. And then you'll recognize K over rho C, that's just alpha, right? So thermal diffusivity. And so then from here, I can write this guy, right? So this is the BO number. And then this is, oh, there needs to be a time here, right? So there's a T here that didn't get propagated into here. So there's a T here, and that's the Fourier number. So ultimately, it's the BO number times Fourier number is equal to this exponent, which is the exponent from lumped capacitance. Okay, so now we've got a definition for the Fourier number. There should be a T here for time. I'll correct the slide when I finalize it. And we can rewrite our lumped capacitance as basically theta over theta initial is equal to the exponent of minus BO number times Fourier number. All right, so, and I should mention, if I didn't say it already, Fourier number is a non-dimensional time that characterizes transient conduction problems. And for lumped capacitance, this is the expression that's based on Fourier number instead of time. Now, if you took fluids with me, you hopefully remember that I am a big fan of Buckingham Pi dimensional analysis, and this equation is completely dimensionless, right? So, right, there's no dimensions here. This is a ratio of temperatures, so units cancel out. BO number is unitless, Fourier number is unitless. They're multiplied together, so two unitless things multiplied together is another unitless thing. So this equation is actually, so think back to fluids, this is the functional relationship between the BO number, Fourier number, and the temperature ratio, right? So if you were to actually carry, we're not gonna do it because we don't talk about Buckingham Pi in this class, but if you were to put together the set of important experimental variables, and then you were to do like the Buckingham Pi analysis, what would pop out is this exact expression, right? So this temperature ratio, and then the BO number and the Fourier number. Of course, you wouldn't know the functional relationship from the Buckingham Pi theorem, but you could run an experiment to figure it out. But I think it's just super cool, right? This shows up in heat transfer. It shows up in fluids. It shows up all over the place. That you basically can write these, very, very real, physical, tangible processes in terms of dimensionless numbers, and those same combinations of dimensionless numbers show up when you do dimensional analysis. So just a cool little thing that you know I wanted to mention since we're here and we've got a dimensionless equation. Um, should mention also, since we have a dimensionless equation, you can use this for similarity analysis, right? So if you have two systems that have, maybe two spheres that are like different diameters or something like that, and you're able to measure the cool down time of maybe the smaller of the two spheres, you can use a similarity to figure out the cool down time of the larger sphere without ever having to take a measurement, right? That's the power of Buckingham Pi. So just want to mention that because it's, I think, a cool feature. Okay, so um, now we go into what the book calls general lumped capacitance analysis, which is kind of this big, ugly equation, which is here, that has in it all of the different ways that an object can either absorb heat or give off heat. And so we say here the processes beyond convection, for example, radiation, also change internal energy and hence the temperature of solids, right? So we want to kind of expand our model beyond just convection to be able to include things like radiation, internal heat generation, and so forth. So internal temperature can be influenced by simultaneous convection, radiation, applied surface heat flux, and internal energy generation. So we have, again, this kind of general expression that accounts for all of that. And so if you sort of imagine like how this gets created, I won't derive it for you, but you can imagine. So initially, we have a solid, which is at temperature T initial, which differs from the fluid temperature T infinity and the surroundings T surrounding. So here's our object, right? Here's the surrounding temperature. Here's the fluid temperature over it. It has some internal energy, so it's got its own internal temperature. Okay, so when surface um, QS, so that's this surface, and volumetric heating, so that's any heat that gets generated, for example, by running current through this or having to undergo, radioactive decay, any sort of generation term. Volumetric heating are initiated. Heat transfer can occur at ex- huh, mutually exclusive surface. I should say surfaces, mutually exclusive surfaces, right? So we can actually have heat transfer off of multiple different surfaces. Moreover, although convection and radiation are prescribed for the same surface, the surfaces may actually differ, right? So it's possible to have convection and conduction or convection and radiation off the same surface. It's also possible for radiation to kind of move somewhere else and for you to be radiating off of some other surface. And so it turns out that when we're defining the surface relative to convection versus relative to radiation, we have these two different terms, ASC and ASR. But when we represent them in the equation, we just write them in a compact form, AS times CR, right? So this represents these two different areas, but just written, compactly as one, instead of having to write this equation multiple times, depending on whether you've got radiation dominating or convection dominating. So for this system, then, with all of this kind of built-in nuance, this is what the first law of thermodynamics returns for us: is a version that has like an internal heat generation, um, energy, um, convection, radiation, and then the thermal mass and the temperature change. So all together. Okay, so now that we have this big ugly equation that's basically got um, surface energy flux, change in internal energy of the system, um, generation, convection, radiation, everything, we're going to simplify it and write various expressions that are useful in particular situations. So one situation that the equation is useful is for radiation. So if you have just radiation and no other form of heat transfer, if you go back to this original equation, this is the radiation term right here where you've got those fourth level exponents, fourth power exponents. Everything else is either zero or negligible compared to this term under this construction. And so all those other things relative to the radiation term drop out. I can do the same thing that I did before to get the original lump capacitance expression, which is to take everything that's a constant and put it on one side of the equation with d time, and then take everything that's temperature and put it on the other side of the equation. And what I end up with is this guy, um, which, although it looks ugly, right, because we've got these temperatures of the fourth power in the denominator, it can actually be solved, right? So here is the closed form solution to this differential equation with all of the terms already built in. So, hey, you're welcome. Okay. I do quickly want to mention, I put this down here in the corner just to remind myself of this. In chapter 1 of the book, when we talked about radiation, there was a little note about a equivalent um, an equivalent convective coefficient for radiation, basically. And what it is just the emissivity of an object times the Stefan-Boltzmann constant times the temperature to the third power. So this is just a reminder that we've seen this expression before as a way of expressing the heat transfer coefficient, if you will, for radiation in terms of something that we recognize as a convection coefficient, right? So that's just to remind me to say that because it's going to come up in a second. Okay, so we have our expression here for temperature as a function of time. This one's actually time as a function of temperature, right? So you plug in whatever the temperature of your object is at a particular moment to this expression, and out will pop the time that it took to get there, right? Or you can solve this in reverse, but it's not set up that way. Okay, so we've got this expression, and now consider the limiting case where T surroundings, right? So we're imagining the surroundings are just like, far away, but we're radiating to some surface that is represented by T sur, so it has its own temperature. But what if you're actually out in space and you're radiating to deep space? Deep space, pretty darn close to zero, right? It's microkelvin is its temperature. So for engineering purposes, we just set that equal to zero, plug it into this equation. Notice that zero shows up a couple times, right? Like in the denominator, which, of course is bad. But if you go back up to where this was derived from, you can see here that it's t surface to the fourth minus t to the fourth. And so if this goes to zero, this just becomes dt over t to the fourth, which can actually be integrated. And what pops out is just this, right? So much simpler version of the same expression where we still do have a couple of temperatures raised to the third power kind of trapped inside the expression, but you can plug in the initial temperature, the final temperature for this configuration to figure out how much time passed for an object that's just radiating to some surface at constant temperature, or radiating out to space in this case. Okay. Another possible permutation is we just did lots of radiation. Now we're doing no radiation. So if the radiation term goes away, let's go back to the big ugly equation. If the radiation term goes away or is just dominated by the convection term, then we get this, right? So notice that radiation is gone, but I still have all the generation terms are in there. This equation, if I remember my law of conservation of chalk for theta, right? That's my definition for theta. I can rewrite this, right? So here's theta, and then here's the derivative of theta. I can rewrite this expression just as d theta dt plus a theta minus b is equal to 0, right? So just simplified it down. And the way that I simplified it down was just to say, okay, a is this collection of variables, b is this collection of variables. None of them have a temperature in them. None of them have a time in them. They're all going to be constant. And so I'm just going to represent them as a and b, solve this guy for theta as a function of a and b, and then if I want to, I can go back and remind myself what a was, what b was, and then plug in all the values and clean up the mess that I've created. So that's basically what I'm doing here. That's where a and b come from. They're just substitutions for more complicated constellations of variables. Okay, so if I carry out this solution, I get solutions of the form theta minus or theta divided by theta I equal to e to the minus alpha t. I think that's a t plus b divided by a over t1 minus t infinity times 1 minus e to the minus at, right? So this is the ultimate expression that I get from solving this form of the equation and then plugging in my value for A and my value for B, which I had to extract to make this kind of easier to track. Okay. There's yet another possibility, which is if we have a variable convection coefficient. It turns out that in free convection, which is if I just have an object sitting out and it's hotter than the environment, and so it starts just getting convection over it because warm air rises, and so it's just warm air rises above the object and then cooler air gets sucked in to replace the warm air. That's free convection. We'll, in theory, talk about that later, although we may run out of time. This also occurs in boiling, which hopefully you've seen. So H varies with temperature difference between the object and the fluid. In these situations, H can be approximated by this equation. I left all of the different kind of dimensional caveats here. So N in this case is constant, and units of C, this leading heat capacitance. It's actually, okay, it's units of conductivity. Sitting here out in front, has this sort of unusual unit structure, right? So it's watts per meter squared Kelvin, which you're used to, but Kelvin gets raised to the 1 plus n power. And that's because the units for this temperature difference are Kelvin. And if I don't raise that to the 1 plus n power, I'm going to have a unit mismatch between the left side and the right side of the equation. So that's what I mean by 1 plus n. If you do choose some value of n that you know greater than what it should be. Sorry, hang on. Yeah. Then you do have to account for the fact that you've just added like extra kelvins, and so you need those extra kelvins to cancel out, right? So that's just what that means. Okay, and so if we've got this as our expression for temperature difference, which of course, as we said, is variable, and if radiation, Q double dot and Q dot are negligible, so that's the internal energy term and the volumetric term, this expression is what pops out, right? So ratio of thetas, and then we've got theta I here to the n on the inside. So it looks kind of like the exponential equation that we had before, except it gets raised to the -1/n power instead of having a bunch of internal terms that you solve for. Okay, so we've got variable convection kind of worked out in terms of an equation. Okay, so we're now ready to just do a couple of examples, and these are not very painful, pretty quick. So we have a steel ball, 12 millimeters in diameter. It has all of these properties: thermal conductivity, density, specific heat. Those are all given. And we're going to anneal this ball by first heating it up to 950 Kelvin and then slowly cooling it to 410 Kelvin in an air environment. And we know that the ambient air in whatever room this is happening in is 325 Kelvin. The convection coefficient that we get is 20 watts per meter squared Kelvin. And we're asked to estimate the time required to cool from 950 down to 410. Yeah. Okay. So, a couple of assumptions before we start. So, one is we're going to assume that convection dominates heat transfer. And what that means is that instead of using, this monster that's got all of these different ways for heat to leave the system in it, we are just going to use this guy, right? So just lumped capacitance without all the extra bells and whistles that get added on. There it is. Okay. So that's what this first assumption means. And the second assumption, properties are constant. That is, this steel ball is going to change temperature, and we're just going to assume that things like K and rho and C don't change as a function of temperature. In reality, they do, but over this temperature range, it's not an enormous difference. And so probably okay, at least as a first estimate. And I do say the word estimate here to just assume that these are all constant. Okay, so we're required to estimate the cooldown time. So the very first thing I'm going to do, the very first thing that I always do when I've got a transient heat transfer problem, is I'm going to check the BO number, right? Make sure before you do lump capacitance that the criteria actually matches. So I'm going to plug in, here's my BO number expression. Remember, I've got a sphere. And even though L sub C for a sphere, from what the textbook says, is the radius over 3, I use a more conservative approach to BO number, which is I'm just going to take the radius of the sphere. Yeah, which is right here, right? So H times the radius of the sphere divided by K. The sphere is 12 millimeters, right? So its radius is 6 millimeters, 0.006 meters. H is given as 20, K is given as 40 watts per meter Kelvin. So I know everything, so I can plug everything in, and what I get when I do the math is 0.003 is my value, and that is less than 0.1, right? So that gets a green check, indicating that I can, in fact, hallelujah, I can use the lump capacitance model to solve this temperature profile. The resulting temperature that I get at the end is, relatively small in terms of the error from the real value. Okay, so here I am doing it, right? So I'm gonna just take my expression theta initial over theta. Oh, okay, we got to flip that over. It should say, right? Because where does this come from? Oh God, did I do it on this slide too? Okay, I'm gonna check that slide as well. It came from here, right? So it should be, in fact, it really came from here, right? So theta over theta initial. I believe that's what it should be. So I'll fix that when I post the slides. Is equal to E to the minus HA over rho VC times T. AS and V, This is the surface area and the volume of the sphere. Those are related to each other by the radius. So I can do a little bit of math here to get rid of those terms and just express their ratio as R naught over 3. And I'm interested in the amount of time that it takes to cool down. So I'm going to remember to get here, I had to exponentiate everything. I just undo that, right? So I'm just going to do the reverse of it and get here, solving for t. Okay. And then I just plug in numbers, right? So, pretty painless. So V over A is R naught over 3. Density is 7,800. What did I do here? Okay. Let me fix that as well. There's an extra copy of 600 joules per kilogram Kelvin, and then rho VC ended up here, and it should have been taken away. And then in the denominator, we have just H, which is given as 20 watts per meter squared Kelvin. And then here is the natural log of the final temperature, right? The temperature of the time that I'm interested in, minus the temperature at infinity of the fluid, and then T initial. This is the initial temperature of my sphere, 950 is what I heated it to begin the problem, and then 325 is T infinity, right? So with the exception of this little mistake here, this should be correct. And when I crank through the math, I get 934 seconds, which if you divide by 60 corresponds to 15.56 minutes, which is what the book says it should be, right? So that worked out. Okay. Let's do another example. This is the last one, and then we'll wrap up. This is actually a textbook example, but the reason that I picked it is because Dr. Sanjay Kim, who's a new faculty member in our department, actually studies this as part of his research. And so I'm like, oh, that's very interesting. We could do a textbook problem that relates to Dr. Kim's research. Cool. Okay. So we're interested in cooling space stations. I guess we are not. Dr. Kim is interested in cooling space stations. And you have to dissipate the heat from the space station in some way. The only thing that you can do, because you don't have any air up there, is dissipate through radiation. And a lot of times radiation is not fast enough, right? Radiation gets multiplied by the Stefan Boltzmann constant, which is a really tiny number. And so you might need more heat transfer to basically dissipate the energy that you're consuming on a power station. And so a power station on a space station, there you go. And so Dr. Kim proposed this unique heat rejection scheme called liquid droplet radiators, LDR. And what happens is warm, high vacuum oil, so oil that can withstand the vacuum of space without evaporating away, is injected into space as a stream of small droplets that traverse a distance L, over which it cools by radiating to outer space at absolute zero temperature, right? So in other words, we have all these little droplets that are coming out at some initial high temperature, and then they're traversing some length L, and then they're getting captured by a collector, and over that traverse from the droplet injector to the droplet connector, they're radiating energy, losing energy to the environment, which is in this case assumed to be, I think, space at 0 Kelvin. And then they get collected here at the end and they're cooled down, and then you can just run them back through over here, run them again, and you can dissipate heat from whatever your space-based system is in that way. Okay, so we have LDR droplets, again, high vacuum droplets that don't evaporate in the vacuum of space. They have an emissivity of 0.95. Here's their density. Here's their specific heat. Here's their thermal conductance. And then here's their diameter, 0.58 millimeters. So really, really tiny. These get injected at 500 Kelvin at a velocity of 0.1 meters per second. And then we're going to make an assumption that the droplets are actually radiating to space at 0 Kelvin, not to the sun or a planet or the spaceship or something else that's there. They're truly radiating to space. And then we're asked to determine L um, required for droplets to impact the collector at 300 Kelvin. So they basically have just given up 200 Kelvin from 500 to 300. So how much thermal energy is rejected by each droplet is a question you might ask. I did just quickly want to mention, because I didn't say it before, this thing down here is the liquid droplet radiator, right? So I've seen Dr. Kim give presentations. This is the graphic that I could find on his website, but he's actually given presentations where this is like a little gun that's like shooting um, droplets, and then they're getting collected. You can actually see it very small here, shooting droplets, and then the droplets are getting collected and they're radiating to the environment as they're moving. Okay, so what's that distance L? What's that distance from the injector to the collector that these particles have to travel to get successfully collected is what we're asking. Okay, so determine L required for droplets to impact the collector at 300 Kelvin. And then we're asked how much thermal energy is rejected by each droplet. Okay, so I'm going to assume no return radiation from space. These things are radiating out into space, but they're not absorbing any energy. And we're also going to assume that even though their temperature drops significantly, their properties are constant, right? So these given emissivities and densities and thermal masses and so forth are all constant despite a significant change in temperature. Okay, so how do we approach these problems? Well, anytime you have a transient problem, the first thing that you must do is check the BO number, right? Always check the BO number. Always be checking the BO number. It's the first thing you do whenever you have transients, because if the BO number is less than 0.1, then hey, you're lumped capacitance and you can do the math really easy. The whole thing is spatially uniform in temperature. If the number is greater than 0.1, then you have to go to a more sophisticated technique, which I'll talk about in follow-on lectures. Okay, so my approach here is to check the BO number for one of these droplets to see if they maintain an internal temperature gradient or whether they are constant temperature all the way through. And if they're constant temperature all the way through, then it's much easier to figure out how far they have to go to get from one side of this collector to the other. So I'm going to use that trick that I showed you right here, right? This equivalent convective resistance associated with the temperature raised to the third power. That's from chapter 1 of the book. And I'm going to use that to find H for two different cases, right? So I might as well do it. So I'm going to find H for the case where the droplet is 500 Kelvin coming out of the injector, and then also the case where it's 300 Kelvin entering the collector, just to see what happens if during this traverse, the BO number drops, I shouldn't say drops, gets high enough that it's bigger than 0.1, in which case you can no longer use lump capacitance, right? So that's basically what I'm doing here by checking two different H values or the BO number of two different H values. I'm just making sure that for both the injector and the collector, I've got lump capacitance, right? So that's what I'm doing here. Okay, so I'm now going to use my remember this radiating to space expression, right? This radiating to space expression that came from that big ugly first law, where I was applying all of the different ways that I could change the temperature of this object, put it all into one equation. Well, I'm going to use that equation. It actually does get used. And there it is. Plug in what I know and try to solve for this, the temperature. Sorry, not the temperature, the time. So what time are we talking about? It's the time for a droplet to traverse from here to here, characterized in this case by the time it takes the droplet to get from whatever its ejector temperature is to whatever its collector temperature is. And they measure that very, very precisely. So they know those for all the droplets. Okay. So here I am plugging in, right? Here's density, here's volume. Oh, no, there's no volume. Where did the volume go? Volume divided by area is just for a sphere, um, the outer radius divided by 6, right? So V over A is just this guy. And then here's my density, here's my specific heat, here's my number 3, here's my emissivity, here is my Stefan Boltzmann constant. And again, where did area go? Well, area got absorbed into a ratio with volume, and then just ended up right out here, right? So that's where that went. Okay, and then 1 over the final temperature raised to the third power minus 1 over the initial temperature raised to the third power. I crank through the math, and I get about 29 seconds. And then the velocity of the droplets were given somewhere. Yeah, here it is. V is equal to 0.1 meters per second. Okay, so I know the length now, right? Because I know the velocity, I know the time of flight for a droplet. So it works out that that distance is about 3 meters, 2.92 meters. And that checks out with what's in the book. We've also been asked to determine how much thermal energy is rejected by each droplet. And so I know the start temperature and the end temperature of the droplet, and I can figure out its mass and specific heat. And so I can use that in combination with basically first law of thermodynamics to get the amount of heat that gets rejected in a single drop from this temperature to this temperature. So all I have to do is find the mass. The mass is just the density times the volume. So here I am just carrying out the volume calculation for a sphere. Here I'm multiplying by the thermal mass. Right here I'm just doing some of the background math. And then putting in this temperature difference, 500 minus 300, and then carrying out all the math. And what I end up with is 0.0344 joules, right? So, you know, relatively tiny, but probably better than using that same surface area to just radiate. You're radiating, but you're dramatically increasing the surface area by radiating off of all these little droplets. Okay, so that's it. That brings us to an end. There's my closing slide. So I want to thank you for your time and attention, and I will see you in the next one. Thanks.